These are the solutions to the homework problems which were due on the virtual day. That's the Friday before spring break, March 18th. So I've scored those. A lot of people didn't do them, so I wanted to make sure that you actually at least understand how to do those and post solutions. So I put the Newton's 3 laws of motion up here. First law of inertia, we've talked about. An object in motion stays in motion. An object at rest stays at rest unless it's acted out on by an unbalanced force. Second law of motion is the law of acceleration. Well, you should have had that on your formula sheet now. It's formula 5, I believe. So an object's acceleration depends on the amount of unbalanced force and the amount of mass. More mass, the lower acceleration, the greater the unbalanced force, the greater the acceleration. We haven't yet talked about the third law of motion very much. That's the law of interaction, and that is that all forces exist in pairs. So each member of a force pair has the same size of force, but the two forces will act on different objects and in opposite directions. So forces are interactions between two objects. For example, if your fist pushes on the wall would push back on your fist in the opposite direction with the exact same amount of force. So this third law of motion is something we'll talk about a little bit more in class. Each of these exemplifies one of those laws of motion. So if this spacecraft is in outer space and it keeps moving at the same speed, that's an example of an object in motion staying in motion without any extra force. So that's an example of Newton's first law of motion. A fighter jet, the exhaust goes backward as the jet moves forward. So basically the burning of the exhaust pushes the gas backward, and the equal and opposite force is pushing the fighter jet forward. If you have a mass and a net force, getting this to accelerate down the road, that is an example of Newton's second law of motion in the formula which we have up here. In terms of the other ones, what's the mass of an object that weighs 980 newtons on Earth? We're going to rearrange this. So a weight is simply a gravitational force. That's force over acceleration is equal to mass. 980 newtons over 9.8 meters per second is 100 kilograms. Converting that to grams, which hopefully you should be able to do, since we've talked about metrics quite a bit, would be 100,000 grams. Now, one of the things with this is if you divided it by 10 meters per second, that's perfectly fine. That's a reasonable amount to round things to. So that'd be 98 kilograms here, 98,000 grams here. If a lunar lander has a gravitational force of 17,500 newtons on Earth, what's its mass? Again, rearranging this Newton's second law equation to solve for the mass, around 1,786 kilograms. If the lunar lander has a weight of 30,050 newtons on the moon, what's the acceleration due to gravity on the moon? So I'm rearranging this. It really should be acceleration is force over mass. So that'd be 1.7 meters per second as gravity's acceleration on the surface of the moon. A bird flies into a window with a net force of 15 newtons. The bird has a mass of 0.15 kilograms. What rate was the bird accelerating into the window? Technically, it's a negative acceleration because it'd be slowing down, but that would be 100 meters per second. Notice, as always, I'm using general formula, plugging in numbers with units, circling answer with units. An astronaut weighed 750 newtons on Earth. What's the astronaut's mass? Again, rearranging this, around 76.5 kilograms. You could have also gotten 75 kilograms if you used 10 meters per second or 10 newtons per kilogram for the gravitational field strength of the Earth. If the astronaut's in space far away from the Earth and the rocket is accelerating 4 meters per second squared, how much force will act on the astronaut? 306 newtons. Chevy Tahoe's engine puts out 4,500 newtons of force, and the empty Chevy has a mass of 4,000 kilograms. That's actually kind of a low mass for a Chevy Tahoe. What will be his acceleration? So acceleration net force over mass, 2.25 meters per second squared, or 2.25 meters per second. So if we each have 7 people in that Tahoe, that's an additional mass of 75 kilograms times 7. That's 525 kilograms. So now the total mass of the system is 2,525 kilograms. So acceleration is still 4,500 newtons divided by 2,525. So that acceleration has been reduced to 1.78 meters per second. And I did that up front, but that should be down here in part C. 8 was asking you to look at free body diagrams, make a free body diagram, and then actually figure out the tension. So the tension up would equal the gravitational force down in this case. So that gravitational force is m times acceleration due to gravity of the Earth, which is 49 newtons. Again, if you use 10, you get 50 newtons here. So the tension in that rope would be 49 newtons or 50 newtons. Here, I've got 2 strings holding this up. So basically, twice the tension would equal 49 newtons. So that tension would equal about 24.5 or 25 newtons. And notice I'm showing 2 forces acting upward because there's 2 separate strings. So I hope this helps, and I certainly hope you go over this before we have a quiz or test. Thanks.